Hello everyone, welcome to this lecture video tutorial in Calculus 3. Enjoy learning. Hello everyone, in today's lesson we will be discussing about infinite series of negative and positive terms. After watching this whole lecture video, you will be able to understand the idea of alternating series. We will also be discussing about alternating series test, the test that you are going to use to determine if the series is if the alternating series is convergent or not. This lesson also we will be discussing about absolute and conditional convergence, in which ratio and root tests are used in this topic. A lot of examples in this lecture that model different types of situations or problems are presented. These are the things that you will be learning in this whole lecture video tutorial. So without further delay, let's start lesson number 6. Hello everyone, welcome back. This is now our lecture proper. So as you can see here, we will be discussing about lesson number 6, which is entitled Infinite Series of Negative and Positive Terms. So for our first definition, we will discuss what do we mean by alternating series. So as you can see here, you are given a positive term uh, positive term series, okay, uh, for all integers n. Okay, we know that our n here starts from maybe 0 or 1 or 2. May and as you have noticed also that in this notation, as you can see here, this one, this is clearly an what they call this one, an alternating series. So we have a factor here, which is negative 1 raised to the power of n, or negative 1 raised to the power of n plus 1. Okay, so if you expand this to notation, clearly this is an alternating series. So from the word alternating, okay, it alternates the sign. So for this one, for the first one, it starts with negative and then positive and then negative and then positive. And for this notation, it starts with positive, since our n starts from 1. So when n is equal to 1, we have 1 plus 1 is 2. So negative number raised to the power of an even number is, we know that it is positive. Okay, so but if you don't believe it, if you don't believe what I'm saying, let's try to expand the first expansion. Let's say this one, expansion of let's say this one, this first notation. We have negative 1 raised to the power of n, a sub n, where n starts from 1 to positive infinity. Okay, so if you try to expand this, we have, when n is equal to 1, we have negative 1. Okay, negative a1 plus a2 minus a3 plus a4, sorry, a4 minus a5, and so on. Okay, negative 1 to the n, a sub n times a sub n plus, and so on and so forth. Okay, for the second one, we have negative 1 to the n plus 1 a sub n, where n starts from again 1 based on our rotation. So when n is equal to 1, we have 1 plus 1, this this one. 1 plus 1 is 2, so we start with a positive number. So we have a1 minus a2 plus a3 minus a4 plus a5 and so on, minus a6 and so on and so forth, raised to the power of a sub n plus that. Okay, so it's okay, that one. Okay, so clearly the given sequence series is alternating. Okay, so this is what we mean by alternating series. Okay, so for our first theorem, this theorem, as I've said in the introduction, the alternating series test, this test will show you if the given alternating series is convergent or not. Okay, so there are three conditions that you are going to satisfy. Okay, these three conditions: a sub n must be positive, then it is decreasing, number 2, and the limit of a sub n as n approaches to positive infinity is 0. Okay, so these are the what they call this one, these are the three conditions that you are going to satisfy to show that the alternating series is convergent or not. Okay, let me number 1 and number 3 are understandable, but in the second condition, this says that when you say decreasing, it is a decreasing sequence. So there are so many ways on how to what they call it, to show that the given series or function is decreasing. So you can show it this way. You can you can put a question mark and then manipulate. Okay, manipulate that and so on, manipulate at the end, manipulate to show that the sequence is indeed increasing or not. Okay, or the other one is you are going to show that this one, we know that this is a sub n plus 1, which is less than a sub n. Okay, so you can divide both sides by an, this one. So this will become this form. Okay, so if you don't like the first method, okay, this is the first method, method 1, this is method 2. Okay, if you don't like the first method, so try this one. It must be that the expression on the what they call this one, on the left hand side is clearly less than or equal to 1. Okay, so I hope that it will be obvious that the left hand side is clearly less than or equal to 1. But if not, then use method 1. The other method is the method 3. This one, method number 3, is you can let the sequence to be this notation, we know that a sequence is a function. Okay, and then show you are going to show that show that the derivative, okay, of that sequence of this notation, this one, the derivative is less than 0, okay, for all n greater than or equal to some number. If your sequence starts from 0, then uh, if starts from 0, then you have to write this big N as 0. When your sequence start at 1, then you have to replace the big N by 1. If your sequence starts with 2, then replace N by the big N by 2. Okay, so that's how you are going to show. There are three methods that you are that you can choose to show that the sequence is decreasing. Okay, so that's how you are going to use the what they call this one, the alternating series test. Okay, so let's have our first example. Let's wait for the program to respond. Do we have an internet connection? As you can see here, we have indeed. So for our first example, let's say let's choose color, let's say purple. So example 1. Okay, example 1. So since our topic is about alternating series, then of course these problems here or these examples here are under the topic alternating series. So show that the series below, series summation of -1 to the n over times 1 over n squared, where n starts from 1 to positive infinity, is convergent or not. Okay, so first is we have our solution. Let's again what happened. So first is we have to let our a sub n, here to be 1 over n squared. Okay, remember that this factor here, -1 to the n, is not included in the a sub n. Okay, based on our based on the definition. Okay, just look at your definition. Okay, let's choose color black. So solution, so let a sub n to be equal to 1 over n squared. Okay, so first is we have to show that that a sub n is that the sequence a sub n is positive valued. Okay, so this is positive valued. So but clearly say here, clearly a sub n which is equal to 1 over n squared is always greater than 0 for all n greater than or equal to 1. Okay, so remember that the in our given here, our n starts from, our index start at 1. Okay, so that's the what they call this one. That's for the first. The second is we are going to show that the sequence is decreasing. Okay, so this is very much easy if you use the third method. Okay, what happened, letter B, decreasing. So we have to let, or if you use the first method, okay, so we will use method 1. Okay, either you can use either of the three. If you use method 1, you can write as we know that uh, we know that uh, clearly we know that uh, we know that n squared is clearly greater than or equal to n for all n greater than or equal to 1. So since we include uh, equality here, because when n start at 1, we have 1 is less than or equal to 1. But for n greater than 1, so clearly n squared is much larger than the left side. Okay, so but if you recall your what do you call this one, uh, previous topic, remember that where do I put this? Okay, so let's try recalling this idea before in your algebra. If a and b are positive numbers, real number, and a is less than b, then we know that 1 over a is greater than 1 over b. I discussed this last time. If you remember your what we discussed in lesson number 5, I guess, lesson number 5 or lesson number 4. Okay, so we did this. Okay, so this is our a. Okay, our a is n, our b is n squared. So with this, we can write 1 over n is clearly greater than 1 over n squared. Okay, we can reverse. Okay, for all n greater than or equal to 1. Okay, can reverse that, and clearly this is our clearly from here, just wait for the program to respond what happened. So what is okay, clearly this is what they call this. Can we go back a little more? Okay, clearly we have what happened here. Do we have an internet connection, or it is just my laptop? So let's try to, let's wait. A sub our goal is to show that an is an plus 1 is less than an. Okay, so our an here, we know that this is our an, but what is an plus 1? An plus 1 is 1 over n plus 1 square. Okay, so am I correct? Okay, we need to show from here, let's try to put a scratch. Okay, we have to if we substitute this one, is 1 over n plus 1 square, which is less than or equal to 1 over n square. And then so we reverse, we have n, sorry, again, yes, so this is n plus 1. Okay, so in our scratch here, we should start at this one. So I think I have to get an argument here first. Okay, so this is this one, so I have to erase this and then make the reverse method. Okay, so I wasn't able to show that a sub n plus 1 is less than or equal to a sub n based on this argument. Okay, so therefore what I will do here is to erase this. Okay, what happened? Let's wait again. Okay, so I have to erase this. Okay, erase this one, and I use again the black color. Can I use the black color? Okay, so we know that n is greater, this one, this is right. So we know that n plus 1 is really greater than or equal, yeah. If we erase this inequality here, let's wait again, the other one. Okay, but anyway, if we will not include the equality sign, this is all true, but to make it safe, oh, what happened? But to make it safe, uy, what happened? Can I go back? Okay, so to make it safe, if I'm going to erase this that's really the argument, since our n is greater than or equal to 1. And if we try to square, okay, but if you will try to write the equality symbol, it's okay, that's okay. Okay, if you square both sides, okay, it doesn't matter. Okay, for all n greater than or equal to 1. Okay, and then if you use this recall here in the left hand side, if you try to use that, we know that 1 over n squared is greater clearly than 1 over n plus 1 square for all n greater than or equal to 1. Oh, what happened? Okay, that's really a big problem if your computer doesn't respond automatically. So this is true, 1 over n squared over 1 over n plus 1 square, or all n greater than or equal to 1. This is true by this recall, and we know that this is our an. Okay, n plus 1. Okay, so clearly we show that our sequence is decreasing. Okay, therefore a sub n is decreasing. Okay, so that's method 1. If you use method 3, this is the easiest one. So you let your f of n to be a sub n. Then uh, f of n is equal to 1 over n squared. But if you take the derivative with respect to n, what happened? With respect to n, okay? This is negative 1 over n cubed. And this is clearly less than 0 for all n greater than or equal to 1. Okay? Therefore, a sub n is decreasing. Okay, this is much easy than the first method. Okay? So that's how you are going to either choose one of these. Okay? So for the third one, so letter C, you have to take the limit. Okay? Take the limit of a sub n as n approaches to positive infinity. Okay, the limit of 1 over n squared as n approaches to positive infinity, clearly this is 0. Okay, so since it satisfies all the requirements, 3 requirements, therefore the series is convergent. Therefore, by AST, the series summation of negative 1 to the n 1 over n squared, can I move upward? Let's try to move up. Okay, so it's taking time to respond. Let me look at my cell phone. Okay, anyway, this one, where n starts from 1 to positive infinity, is convergent. Okay, so that's how you are going to use the AST, or the alternating series test. Okay, so for our second example, just wait. For our next example, example number 2, we have here, as you can see, example number 2. Let's write it here. Example number 2, again, show that the series negative 1 to the n plus 1, 10 to the n over n to the 10, as your n starts from 1 to infinity by AST. Okay, show that the series is convergent or not. Okay, solution. So first is we have to let our an to be 10 to the n over n to the 10. Okay, then so first let's show that the sequence a sub n is positive valued. Okay, so letter A, positive valued. So again, clearly uh, 10 to the n over n to the 10 is greater than 0 for all n greater than or equal to 1. Okay, that's easy. Letter B, how about for decreasing? Okay, So I think it's easy to show that the sequence a sub n is decreasing using method number 10. No, method number 3. Sorry. Method number 1 and method number 2 is useful if you have a polynomial function. Okay? But if it is a what they call this one, other than polynomial, then use the idea of derivative. Okay, let f of n to be equal to this one, which is our this given here. Then we have f, which is 10 to the n over n to the 10. So you have to get the derivative with respect to n. We can use what they call this one, you can use quotient rule. N to the 10 square. Okay, denominator copy the denominator and derivative of the numerator. So what is the derivative of 10 to the n? So the answer is let's use another notation. ln 10 times 10 to the n, okay, minus 10 to the n times the derivative of the denominator, which is 10 n to the 9. Okay, so let's simplify. If this is really negative, okay, this expression on the right hand side is negative. So how do we do that? Let's factor. It's with the common is n to the 9 and also 10 to the n. Okay, 10 to the n is also common, and the remaining the first term here is ln 10 times, okay, let's write this one, times n minus 10 can I factor out the 10? Okay, that's okay, over n to the 20. Okay, so what will happen? Cancel out. We have n to the 11. Okay, then what remains here is 10 to the n. Can I factor out, let's say, here, can I factor out, that's okay, this is ln 10 times n minus 10. Okay, is this less than, always less than uh, 0, which is always negative. Okay, so that's a challenging question. uh, let's look at the graph. So what will happen if this is 1 million? So meaning to say, when n is equal, if this is always 10 to the n, and n to the 11 is always positive. So the question here is this factor. Okay, in this factor here, if this is always negative for all n greater than or equal to 1. So let's try that in our in the Dismos calculator or graph. ln, let's say, let's write here x ln of 10, ln of 10 minus 10. So what happened? ln 10, so it is positive when it is positive when at this point. Okay, so it is not always negative. So what happened? Am I wrong in getting the derivative of 10 to the n? Okay, so let's pause for a moment. Hello, I came back. As I analyze this expression here on the right hand side, I am not sure that this expression here is less than 0. Okay, not sure. Let's try. Let's move upward. Not sure. Not sure if less than 0 for all n greater than or equal to 1. Why? As you can see in the graph that I've shown you, this factor here 10 to the n and n to the 11 are clearly positive, but this factor, the quantity ln of 10 times n minus 10 is not always negative. Okay, so this is not less than 0 for all n greater than or equal to 1. Okay, so if you look at the graph, okay, if you look at the graph, just graph it in this Dismos graphing calculator, you will see that clearly this is not less than 0. So if you use method 3, then this is not clear if this is less than 0. Okay, so let's try method method 1. Okay, if we will use method 1, the same result. Okay, so if you have a sub n plus 1 question mark a sub n, so if you substitute, we have 10 to the n plus 1 over n plus 1 to the 10 10 to the n over n to the 10. So if you cross multiply, what you will see is, again, it is not clear that this a sub n is less than or equal to a sub n plus 1. Okay, so here we cross multiply, we have 10 to the n plus 1 times n to the 10, 10 to the n times n plus 1 to the 10. What you will see here, if we cancel out this one, we have 10 times n to the 10 question mark n plus 1 raised to the power of 10. Okay, so again, in this scenario, we are not sure that we are not sure if this we are not sure we are not sure we cannot distribute 10. Okay, 10 on the inside of this parenthesis. Okay, you have to use what they call this one, you have to use this distributive method. Okay, we are not sure if 10 to the 10 times n to the 10 is less than or equal to n plus 1 raised to the power of 10. Okay, not sure again. So let's try method number 2. Okay, method number 2. So I will correct this one later. Okay, this is n plus 1. Maybe can I wait for plus 1. So method 2 suggests that we have to show that a sub n plus 1 over an is less than or equal to 1. Okay, again, if you use this method, we are not sure. Okay, so let's try to substitute 10 to the n plus 1 over n to the 10 over no, this is n plus 1. Okay, let's wait. This is n 10 to the n over n to the 10. So maybe n plus 1 to the 10. Anyway, so reciprocal, we have 10 to the n plus 1 over n plus 1 to the 10, n to the 10, 10 to the n. Is this less than 1? Okay, so we can cancel out. So again, we have 10 to the 10 times n to the 10 over n plus 1 to the 10. Okay, is this less than 1? So clearly, if you use this, it may not obvious. It may not be obvious, but if you look at the graph, okay, if you look at the graph, 10, just look at the graph, times times n to the 10, we have x to the 10, x to the 10 divided by x plus 1 to the 10. Okay, divided by the quantity x plus 1 to the 10. Okay, so this is the graph. Okay, if you plot your one here on the left hand right hand side, this is y is equal to 1. Okay, so meaning to say, when your n is greater than this value here, okay, this value here, if you move from the right, then it is clearly the graph is above the line y is equal to 1. So if you take n is equal to 6, okay, if you take n is equal to 6, then clearly this is not less than, the left hand side is not less than or equal to 1. Okay, so that's the idea. So, or maybe here, if you take n is equal to 6, then this is not true. Okay, so you can choose which one. So if we take n which is equal to 6, okay, then clearly 10 times 6 to the 10 over 7 to the 10 is not less than 1. Okay, so therefore a sub n is not decreasing for all n greater than or equal to 1. You can do the same for this. Okay, so just look at the graph here and you will see that it is not decreasing. Okay, anyway, if you look at 10 to the x divided by x to the 10, then clearly from here, from this point, this point here, okay, it is increasing. This area here we have decreasing up to maybe 6 something. So but as you can see, as n approaches to infinity, this is not a decreasing function. Okay, so actually you cannot proceed now. You can conclude now that the series that the series in example number 2 is not convergent. Okay, but if you want to proceed, to show that the limit is also not is equal to 0, then maybe you can try for letter C. So just take the limit of an as n approaches to infinity. You are going to show that this is 0, but actually this is not equal to 0. Okay, so just from here, just use the idea about the the previous topic, relative rates of growth. Okay, I don't know if you remember it, about f of x grows faster than g of x, or g of x grows more slowly than f of x. That's and the previous topic, lesson number 5. Okay, so if you recall, I write this at the, what they call this one, in the previous lesson. that if you are given a number n and m which satisfies this inequality, and your a and b also a number which satisfies this inequality, then I don't know if you ever recall this. I hope you listen to the lecture before this lesson. Okay, let's move upward. uh, Remember that uh, this relation L and X is much faster, is slower than X to the N, and X to the N is slower than X to the M, since our M here is greater than N. But X to the M is slower than A to the X. No? Yes, X to the M is slower. And A to the X is slower than B to the X. And so on. Okay? So basically, in this idea here, we can use this one, A to the X and X to the N or X to the M. Okay? So the numerator here is this one, okay, and the denominator is either this one or this. So the numerator is much faster than the denominator. Okay, so therefore by the definition, okay, by definition, this implies that n to the 10 is slower than 10 to the n. Okay, so from this idea, this means that 10 to the n is much faster than n to the 10. So this is positive infinity. Okay, so again, letter B and letter C of the alternating series test, the series summation of -1 to the n plus 1 times 10 to the n over n to the 10, where n starts from 1 to positive infinity, is divergent. Okay, so therefore, sub conclusion here, therefore by AST, the series summation of -1 to the n plus 1 times 10 to the n over n to the 10, where n starts from 1 to positive infinity, is divergent. Okay, so that's problem example number 2. Okay, for our third example, let's try this problem. Number 3, we have summation of -5 to the n, where n starts from 1 to positive infinity. This is again by alternating series test. Okay, so notice that as you can see, it is not visible in this form in the given that the quantity of -1 to the n, or the quantity -1 to the n plus 1 is present in this given. Okay, so we can simplify this. As first is you have to simplify so that it is clear that this is a alternating series. So what you will do is that this is -n, okay, -n, sorry. So you can write this as uh, negative 1 over negative 5 raised to the power of positive 1 to positive infinity. Okay, so however, uh, if you further simplify the denominator, so you will have negative 1 raised to the power of n times 5 to the n. N starts from 1 to positive infinity. Okay, this is basic. You can recall your algebra here. AB raised to the power of n. This is a to the n times b to the n. Okay, recall. So our a here is negative 1 and our b is positive 5. So from this, you will have summation of doesn't matter if you put this factor, the quantity of negative 1 to the n to this side or in the numerator, it will not vary. Okay, because the answer of this factor here is always negative 1 and 1. Okay, this is 1 over 5 to the n, and starts from 1 to positive infinity. So this is now our simplified form. Okay, so clearly our an here is 1. So first is you have to let our an to be 1 over 5 to the n. Okay, then so letter A, clearly for positive valued, clearly our an, which is 1 over 5 to the n, is always positive for all n greater than or equal to 1. How about decreasing? Okay, for decreasing, I guess the third method is much easy to use. Okay, so let's wait. So let f of n to be a sub n, then f of n, which is 5 raised to the power of negative 1. I simplified it already. This is what we call this, an exponential of the form a to the x. Okay, so if you recall your algebra, this is ln not algebra, your calculus 2, ln 5, this times times 5 to the negative n, then the derivative of n is negative n is negative 1. So this is, if you simplify, this is negative ln 5 over 5 to the n, and this is clearly less than 0 for all n greater than 1. This is obvious. ln 5 is a positive number. 5 to the n is always positive for all n. Times negative, this is always less than 0. So therefore, a sub n is decreasing. Okay, decreasing. So the limit, the third one, clearly the limit is zero as n approaches to positive infinity. Okay, so let's wait for the program to respond. Letter C, the limit of a sub n as n approaches to positive infinity, we have limit of 5 to the n. Clearly this is 0. Okay, so therefore by alternating series test, the original of the given series is convergent. Okay, that's problem number or example number 3. Okay, let's try problem number 4 here. Let's try this color purple. Number 4, we have summation of -1 to the n plus 1 times n factorial, quantity of n factorial raised to the power of 2 over 2n, quantity of 2n factorial, where n starts from 1 to positive infinity. Again, this is by, of course, very obvious. We have a factor here. This is an alternating series. Okay, solution. So we are going to let our an to be n factorial, this one, 2n factorial. Then for positive valued, let's wait for the program again to respond. Early a sub n, which is n factorial, quantity of n factorial square over quantity square is clearly greater than 0, or all n greater than or equal to 1. Okay, letter B, decreasing. For we cannot use method number 3 because we don't have a derivative for a factorial. We did not discuss that topic. Okay, so what we will do here is to use method number 2. Okay, so let's wait. Let's move upward here. Okay, we are going to show a sub n plus 1 over a sub n is less than this one. Okay, so substitute. We have n factorial square over quantity this one, n plus 1 factorial over 2 times n plus 1 factorial over n factorial sorry, I think I have to here square over 2 factorial. Is this less than or equal to 1? That's a very interesting question. So all you have to do is to uh, take the reciprocal on the left hand side. Sorry. Okay, so what will happen here is that I think I have to, this will become the numerator over n factorial, this less than or equal to 1. So what will happen here in the numerator, we have to simplify. This will become n plus 1 times n factorial. Okay, raised to the power of 2. And here we have, in the denominator, you have to simplify 2n plus 2 times the quantity is 1 times 2n plus 1 times 2n factorial. Okay, so what we will do here is that we can cancel out this one, cancel out also this one here. So what remains in the numerator is n plus 1 square over 2n quantity 2n plus 2 and quantity 2n plus 1. So is this clearly less than 1? I guess it is not. So therefore, let's expand the numerator, n squared plus 2n plus 1, which is less than, cross multiply. We have 4n squared, the numerator is 4n plus 2n is 6n plus 2. And then we will have transfer the left side to the right side. We have 3n squared plus 4n plus 1. Okay, so we are almost done. But again, we have to wait for the program to respond. So I guess that we can move up, so we can transfer both sides. We have negative 3n squared minus 4n. Is this less than 1? Question mark. Clearly this is greater than 0, but what we need to show that in the previous, this in the at the top is this, the expression here on the left side must be less than or equal to 1. So I guess this is now obvious. You can factor out negative n. This is 3n plus 4 question mark here. This is clearly less than 1 for all n greater than or equal to 1. Okay, so this is always positive, and then this is always negative here on the other side. So negative times positive is negative. So clearly this is less than 1. So therefore a sub n is decreasing. Okay, so to show the limit, okay, the limit of no, the limit of, where is that one? Sorry, put an X here. Go back. Let's move back. Let's try some a sub n as n approaches to positive infinity. So what is the limit of n factorial quantity n factorial square times 2n, this one, factorial as n approaches to positive infinity. Then what is the limit? Can we move up? So how you are going to show, or what is the limit? So again, let's apply the idea about the relative growth rate of the function. Okay, so what you have to do is to recall your our previous topic. Okay, so before that, let's recall again. Recall the previous discussion. Which is lesson 5. Okay, I will write it here. No, I will not write. I will put an image. But before that, let me tell you that this is the limit of this one is 0. Okay? This is 0. After I will put all those definitions here, this canvas here, you can show that this is 0. Okay, you can this is not your assignment, but do it at home. Okay, do it at home. Okay, show this that the limit is actually 0. Okay, by recalling all these definitions. So I will put it now, the definition. Let's have this one, this definition here. Let's wait. It says here that if this limit, if you satisfy this limit, okay, the limit of f of x over g of x as x approaches to infinity is equal to positive infinity, then this says that f of x grows faster than g of x. Okay, or equivalently, if the limit of g of x over f of x as x approaches to infinity is 0, and this says that g of x grows more slowly than f of x, and we write it in this form. This is not an inequality symbol. Okay, this one. Okay. Yes. Maybe I should stop and then come back later after loading. Maybe I should stop. Okay, so here I've loaded everything. I stopped last time just to load all these images. Okay, so as I've said, do it at home, that the limit of the sequence a sub n, which is this one, is actually 0 by using this following definition and fact. Okay, so I discussed this already. This fact here says that if f of x grows faster than g of x and you are given any constant c which is greater than 0, then it doesn't matter if you multiply c here and c to the function f of x, which is the one that grows faster. It's a faster than g of x if you multiply by c. Okay, and also here what is significant here is that in this notation, okay, this property here, this one, it says that if you multiply again by c at the one that is slower, it doesn't matter. F of x is also faster than c times g of x. Okay, for the second one, fact number 2, this is much like not transitive. It says here that if f of x is faster than g of x, also f of x is faster than f of x, then if you sum g of x, the function g of x and f of x, it will not affect. Okay, f of x is also much faster than the sum of these two. Okay, just study on your own if you have a product. Okay, so this fact also you can use this to show the limit. Okay, at the top. And this one for sequences, this I've already written this one, this inequality here in lesson number 5. Okay, n factorial is much slower than n to the n. Okay? So this is not an inequality symbol, meaning to say that this is not true for some small values of n. This will hold for large values of n, sufficiently large values of n. Okay, so anyway, that's all. We have four examples, and then that's basically how you are going to use the alternating series test. So for your assignment here, this is due on I guess today is Wednesday, so maybe Monday. Okay, this is due on Monday or maybe Tuesday. Okay, so this is your assignment. Let's try color green. Okay, assignment, use alternating series test. Okay, number 1, you have summation of negative 1 to the n times the quantity ln of n over ln n squared raised to the power of n, where n starts from 1 to positive infinity. Number 2, you have summation of this one, cosine n pi over n, where n starts from 1 to positive infinity. Number 3, summation of negative 1 to the n, 2n is the quantity 2n factorial over 2 to the n times n factorial times n. Okay, where n starts from 1 to positive infinity. Number 4, we have summation of negative 1 to the n times the quantity square root of n plus square root of n minus square root of n where n starts from 1 to positive infinity. Okay, so I will put the Google Docs in the uh, classwork menu or classwork window in your Google Classroom to upload all those images. So remember that you have to take the image of your solution for number 1 and then insert that using the insert button. Okay, for number 2 also, uh, take a picture or image of your solution. Okay, so no erasure, and do the same for number 3 and number 4. So for each solution, write your name, your complete details, your name, your our subject, the deadline, and the signature in it. Okay, so make your penmanship clear or more visible. Okay, use bond paper or manila paper for your solution. Maybe long or short, it doesn't matter, as long as your solution is very clear. Okay, so thank you so much for listening. The next topic will be about ratio test and no, not ratio test, but the absolute convergence and conditional convergence, and then we will discuss ratio test and the root test. So maybe we have 2 more videos. This is part 1. We have part 2, or maybe part 2 and part 3 in the next our next topic. Okay, so or maybe I can combine absolute convergence or the conditional convergence and the ratio and root test in one video. So I just have to look into for that situation. Okay, so thank you so much. Don't forget to subscribe to my channel and click that red button and bell button down below in the description. Okay, so thank you so much for watching. Enjoy learning.